We started out in lecture 1 on electrical charge. We talked about electrical forces. We introduced electrical fields. In last class, we talked about electrical flux. And finally, there's a last quantity that we're going to describe in understanding the interactions of electrical charges, and that's electrical potential. So today's class is all about electrical potential, and it's just one more way of thinking about electrical interactions. It's kind of one more, I don't know, screwdriver or wrench in the physics toolbox of thinking about electrical interactions. So in today's class, I wanted to cover this material. So I wanted us to firstly just recall that when we think about interactions between objects or between things, we've learned to think about it from a force perspective, kind of pushes and pulls, and we've learned to think about interactions also from an energy perspective, transfer flow of energy. So we're going to remind ourselves of that and introduce in that way the concept of electrical potential and electrical energy. So I'll then define electrical potential in terms of electrical energy, a bit like how we defined electrical fields in terms of electrical forces. And then we're going to look at the relationship between electrical potential and electrical energy. We're going to look at some examples of electrical potential and electrical energy. And finally, if I get time, we'll say something about conductors and electrical potential. So that's the kind of laundry list of what we're going to try and cover today. Okay, so let's start with this perspective thing, that you can view interactions from a force perspective or an energy perspective, and that's often useful. So this slide here, this overhead here, shows you, or demonstrates the relationship between a force perspective on how things work and an energy perspective on how things work. The key idea is that when you exert a force on something, you are transferring energy to or from that something. And we call that energy transfer work done on that something. So forces act to transfer energy. Forces act to move energy. They may act to move energy from one object to another object as the owner of the energy. They may act to transform energy from one form to another form as kind of the owner of the energy. In this example here, right, this is me. I'm exerting a force, and as I exert that force, I'm transferring energy to the crowbar. And then this is the crowbar. The crowbar is exerting that force, and as it exerts that force, it's transferring energy to the floorboard. And so we can view what's going on here from the perspective of my force and the crowbar's force. We can view it from the perspective of the energy I'm transferring, the work I'm doing, and the energy the crowbar is transferring and the work that it's doing. And so those are the two perspectives, force and energy. Let's look at this example here, which illustrates how we can think from both perspectives. This is one that involves gravity, and then we'll look at a second perspective of the force and energy perspectives where we'll think about electricity. So over here on the left-hand side, I'm thinking of a familiar situation, a falling body, from the force perspective. And over here on the right-hand side, I'm thinking of the same situation, a falling body, from the energy perspective. So here's the apple, and it falls downwards towards the ground. If I'm thinking from the force perspective, then what I'm imagining is that there's a gravitational force, a gravitational pull on the apple from the Earth that's causing the apple speed to increase, causing the apple to accelerate. And so that's my kind of force perspective of the apple's downward fall. If I think of the apple from the energy perspective, if I think of it from the energy perspective, then that apple's fall corresponds to releasing gravitational energy, gravitational potential energy, and increasing kinetic energy, energy associated with the motion. And that release of gravitational potential energy into moving kinetic energy is a transfer of energy, and that transfer of energy we call the work done by gravity. So over here on the left, from the force perspective, it's the force that's speeding up the apple. And over here on the right perspective, the energy perspective, it's kind of the work done that's increasing the kinetic energy of the apple. There's a little equation here that we're going to talk about today. This is the equation for the work done in that energy perspective. So this is the work done by gravity. And the work done by gravity in this situation here at the falling body, well, the work done corresponds to the change in kinetic energy, or the increase in kinetic energy as the body falls. And it corresponds to the decrease, the minus sign here, of potential energy. So gravitational potential energy is lost, kinetic energy is gained, and that loss, that gain, is what we call the work done by the gravitational force. Now, we can think of electricity in exactly the same manner. So this is an analogous slide, now not for a massive apple falling under gravity, but for a charged apple falling under an electrical force. So again, over here on the right, over here on the left-hand side, I've got a force perspective of the falling apple, the electrical falling apple. And over here on the right-hand side, I've got the energy perspective of what's going on. And again, these are two perspectives we can view the situation from. So in this perspective over here on the left, the force perspective, the apple's in an electrical field. The apple is charged and so experiences an electrical force. And the apple is falling, electrically falling in that electrical field. And as it experiences that electrical force, that electrical pull, its speed is increasing, it's accelerating, it's acquiring kinetic energy. So that's the force perspective. Here's the energy perspective. As the apple falls, it's releasing now electrical potential energy. So this electrical potential piggy bank, reserve, that's releasing energy. That's being turned into, downstairs here, kinetic energy, moving energy associated with the moving charged electrons. And that's done, that movement of energy is through the work that's done by the electrical force, this WE here. And so these are two ways, again, of thinking about the situation. Again, there's an equation here, right, that we can apply to this energy perspective. The amount of work that's done, the amount of energy that's transferred by the electrical force, is equal to the extra kinetic energy acquired, so the gaining kinetic energy, that's the delta KE, and it's equal to the loss of electrical potential energy. So the minus sign is that we're releasing electrical potential energy here. And so this equation kind of describes the energy perspective. Okay. So what we're moving on to do is, and you did this with gravity in first semester, is that not just thinking of this force and field perspective, but we're going to think about the associated energies with electrical interactions, like you thought about the associated energies associated with gravitational interactions. Let me demonstrate that there really is electrical energy. I'm going to put the camera on. So on this stick here is a neon lamp. It's like a fluorescent lamp. We don't see so many fluorescent lamps now, but this is a neon fluorescent lamp. Now, if I was to try and light that lamp, I would normally connect a wire on the left and connect a wire on the right and plug it into a wall socket, and we could light that lamp. That lamp needs some energy to light up. And by connecting the wires on the left and right and connecting them to the wall socket, I'm providing that energy. But actually, an electrical field of an electrical charge is a store of energy. So that field that surrounds a charge is also a store of energy. And I'm going to light this lamp by not connecting it to the wall socket through two wires. I'm going to light this lamp by just putting it in a region of electrical field. And that field contains energy. That field supplies energy. And we're going to try and light this lamp. So I'm going to make the electrical field with the Van de Graaff generator here. So if I set it running, it's going to accumulate charge upstairs here on the metal sphere. And surrounding that charge, we now know to imagine, we now know to visualize, right, this field that is expanding outwards through space, everywhere through space from that charge. It's going to be real strong, close to the metal sphere. It gets weaker further from the metal sphere. But it's really a real thing. It is a real thing that's surrounding this charge. And then I'm going to immerse this lamp just in that field. And we're going to see if we can light it from the energy that's in that field. So I'm going to set the mood by turning the lights out. And I hope you can see it's this sort of yellowy, orange, tangerine light of the neon. And look, I'm not connecting the fluorescent lamp to anything. It's not touching anything, but it's being lit. It's being lit by energy that's in this electrical field. So if you wanted a demonstration that this is a real electrical field, that it contains energy, I think this is a clear demonstration. Okay. Okay, so now we know that there's energy out there. There's energy out there in electrical fields. All electrical fields are storing energy. They're all a kind of reservoir of energy. And we're going to now get a bit more mathematical, a bit more quantitative about that electrical energy. We're going to introduce not only the idea of the electrical energy, but a related idea of the electrical potential. And we're going to introduce the electrical potential. I want to put the lights back on, don't I? That didn't do anything. didn't do anything either. I have no idea why I can't turn the lights back on. That seems so ridiculous. And turn that one on. Why did I? Oh, here we are. Maybe I just had to wait. Maybe, yeah. I have this problem with patience sometimes, and I think there was maybe a lack of patience with the lights. But now I've sidetracked myself, and I don't know what I'm doing either. We're going to introduce the electrical potential. And I'm going to introduce it in the same way that I introduced the electrical field. We introduce the electrical field by connecting or relating the electrical field to some more concrete things, or measurable things, because the electrical field was rather abstract. We're going to introduce the electrical potential by relating it to more concrete things, measurable things, because again, the electrical potential is a little bit abstract. So this is a slide we met a few classes ago. It's how I introduced the electrical field. So I said, imagine a source of electrical field. It's this source charge over here. Imagine I take a probe of the electrical field. It's this test charge here. And I put it in the field of the source charge. I define the electrical field, E, in terms of the test charge's charge, that's the Q naught, and the force the test charge experiences. So these are two measurable, observable, concrete things. The charge of this test charge, the force on this test charge. Together I use those to define the electrical field at the location of the test charge. It's really how I see the electrical field at this location. So that's how we define the electrical field. This is how we define, in a similar way, the electrical potential. So again, imagine I've got a source charge over here on the left-hand side, and it's the source of some electrical field in the surrounding space. Then I'm going to take my probe, this time it's going to be a probe of the electrical potential, and I'm going to take that test charge, that's going to be the probe of the electrical potential, and I'm going to walk it into the field of the source charge. So I'm going to walk it from some distance that's, say, far away. This is I for initial position. To some distance that's closer by. This is F for final position. I'm just going to walk it across the bench top here towards the Van de Graaff. So that takes some energy to carry that charge into that electrical field. Okay? There's going to be some change of energy in that charge by moving it from outside the electrical field to inside the region of the electrical field. We define the electrical potential difference. So this is the change in potential between these two locations, I and F. We define that as the change in potential energy when I move this charge from this location on the right to this location on the left, divided by the amount of test charge, the value of the test charge. So again, we're introducing a new quantity, abstract quantity, its potential, or change in potential. We're defining in terms of measurable things. This is the amount of energy I had to supply to move the charge in towards the source charge. And this is the charge of the test charge. And so these are the measurables. This is the new abstract quantity. And so that's how we define potential. And it's really a mirror of how we define field, and it's how we define electrical potential and electrical field, two abstract but important quantities in describing how electricity works in terms of more concrete things like the force, the push and the pull on a charge, or the energy to move to and fro, the work you have to do to move the charge to and fro. We're defining the E and the V in terms of real, physical, measurable, observable things. Okay. So a couple of points about the electrical potential in comparison to the electrical field. Firstly, a big point is they are both abstract, but they are both real, right? They're not just things we're making up to help us solve the problems. We now know both of these things, E and V, are real. They are real entities. They're not made of material, they're immaterial, I would call them, but they are real. They're not just imagined. Every charge is surrounded by an electrical field and electrical potential. It's a real electrical field and potential. Now, here's a couple of important points. So when we talk about the electrical field, we can talk about the electrical field at a single point. I can tell you that it's 1,000 newtons per coulomb at this point, or 100 newtons per coulomb at this other point. When we talk about the electrical potential, the only thing that's physically significant is actually the change or the difference in electrical potential between 2 points. So that's a bit more complicated than our language for the field. The only thing that's physically significant for an electrical potential is potential differences. Potential differences between two locations, between 2 points in space. Now, that has a consequence. The consequence is the following, that you are free to choose the electrical potential to be 0 at any point you like. So on the one hand, that sounds, well, nice, I like freedom. On the other hand, that sounds like, in physics problems, I don't want that freedom. But you are free to choose the electrical potential to be 0 anywhere you like, because all that matters is the difference between the potential at one place and some other place, between some other place and where you chose it to be 0. All that counts is that potential difference. So as an example, a couple of examples. Often we're dealing with point charges. So if I'm dealing with a point charge, it's often very convenient to imagine that the potential that surrounds that point charge goes to 0, vanishes at very large distances, infinite distances from the point charge. We normally do that. So we normally, when we think about electrical potentials of point charges, we think about the 0 of the potential being far away, infinitely far away, and then quote the potentials around the charge with respect to that 0. Another case that comes up a lot, we've already talked about, suppose you've got 2 charge plates. One's positive, one's negative. Here's the positive plate, here's the negative plate. In that situation, we tend to choose one or other, left or right, to be a location of 0 potential. Again, the only thing that counts is the potential difference of any location from that 0 potential plate. And so you can make that choice, and that often makes your solution to a problem, your solution to a question, more straightforward, to pick one or other of these plates as the 0 potential. Okay. Well, we've introduced electrical field, and we've introduced electrical potential. So we now, whenever we picture a charge, right, we're picturing that it is a source. It's always a source of electrical field around it throughout space, electrical potential around it throughout space. Are these two kind of distinct things that both come along with the electrical charge? I would say that they're two very related things. They're two alternative ways of thinking about the charge's influence on the surrounding space. So I want to look at the connection, relationship between electrical field E and electrical potential V. Let's see how that works. And this slide shows you that connection. So in this slide, I've arranged for a positively charged plate over here on the left-hand side, a negatively charged plate over here on the right-hand side. We've therefore got field lines, electrical field lines, that sweep out of the positively charged plate on the left and end up on the negatively charged plate on the right. So here's our uniform electrical field and the field lines that describe it. And then we're going to place a charge, Q, in that field. We're going to start it out near the positive plate, and we're going to let it move towards the negative plate. And we're going to think about this motion of this charge from the left to the right in the electrical field from an energy perspective. And by thinking of it from an energy perspective and our relationship between the energy and the force perspective, we'll find the relationship between the energy and the field. Okay. Let's start here. This equation here says that when we move this charge from the left to the right, there'll be a change in stored potential energy, electrical potential energy. And that change in stored potential energy, electrical potential energy, is equal to the negative work that's done by the electrical force. We met this relationship earlier. And the negative work that's done, or the work that's done by the electrical force, is equal to force times distance. And so I just plug that in here. So this is the relationship between energy and force for this electrical situation, this electrical problem. Now, I can plug in on the left-hand side, I'm plugging in the definition of the electrical potential. Remember, we defined it in terms of the change in electrical potential energy on some sort of charge. And here I'm plugging in, over on the right-hand side, the definition of the electrical field. And remember, we define the electrical field in terms of the force on a charge and the amount of charge. So I'm just plugging those two equations in, those two definitions in. That's all I'm doing here. What I'm doing is replacing potential energy on the left with electrical potential. I'm replacing the force on the right with the electrical field. I get this little relationship here. If you plug in this equation on the left for potential energy, this equation on the right for force, you get this equation here. This equation, if you rearrange it, says the following. And this is kind of the important point here. It says that the electrical field is the negative slope of the electrical potential. So that field that surrounds a charge, that potential that surrounds a charge, they're deeply connected quantities. One is the negative slope of the other. The field is the negative slope of the potential. And so that's how we think about how the field and the potential are related to one another. One's simply the negative slope of the other. The field's the negative slope of the potential. You can, state that in words. I did that here. Or this equation is stating that as a formula. Look, here's the field on the left, and here's the slope of the potential. It's the change in potential in some distance. Delta V over delta X is the slope of potential. And here's the fact that the field is the negative slope of the potential. And it all popped out of us thinking about the relationship, the connection between the force and energy perspectives in an electrical situation. So it just naturally emerged from our definitions of field and potential. Okay. Let's look at an example of this relationship. between the electrical potential and the electric field. So on this graph here, I'm picturing horizontally space, location in space. So I called this the x-axis. So imagine walking up and down the x-axis. And I'm plotting vertically, I'm plotting the electrical potential as a function of your location in space. So I'm walking from the origin, 1 centimeter, 2 centimeters, 3 centimeters, 4 centimeters, 5 centimeters. And as I take that walk from the left to the right, I see that the potential, the electrical potential V, is changing. So look, as I walk to 1 centimeter location, it's growing from 0 to 30 volts. As I walk from 1 centimeter to 2 centimeter location, it's decreasing from 30 to 0 volts. As I walk from 2 to 3 centimeters, it's 0. The electrical potential is 0, and so on and so forth. So this is a map of the electrical potential in some region of space due to some arrangement of charges. The question is, what's the electrical field in that region of space corresponding to that electrical potential? Well, we just said that the electrical field is the negative slope of the electrical potential. So if I know the electrical potential, I can look at the electrical potential and say, what's the negative slope? In this region here, from 0 to 1 centimeter, what's the slope? Well, the change in potential is 30 volts. The change in position is 1 centimeter. And so the slope is 30 volts over 1 centimeter. The change in the y-axis divided by the change in the x-axis. The change in voltage divided by the change in position. So it's 30 volts per centimeter. Now, it's an upward slope, an uphill slope. So that's a positive slope. But remember, the field is the negative slope. So the field is going to be minus 30 volts per centimeter. And so I'm able to read off the field in this region from the potential by recognizing that the field is the negative slope of the potential. We can do the same thing over here between 1 and 2 centimeters. So between 1 and 2 centimeters, the electrical field goes from 30 volts to 0 volts as you walk a further 1 centimeter. So the slope there is the change of electrical potential. That's minus 30 volts. We went down. Divided by the displacement, that's 1 centimeter. So the slope is minus 30 volts per centimeter. But we've got to remember, again, the electrical field is the negative slope of the potential. So the negative slope of the potential is actually plus 30 volts per centimeter. And so this region here has an electrical field that's plus 30 volts per centimeter. These two fields are the same size, same strength, but they're in opposite directions. One's in the positive, one's in the negative x direction. What about in this region here? When this region here, if we walk from 2 to 3 centimeters, then the initial potential is 0, and the final potential is 0. It's always 0 in that region from 2 to 3 centimeters. So the potential has changed by how much? Delta V is 0. There's no change in potential as we've walked 1 centimeter. So if I was going to calculate the slope, I'd have 0 volts over 1 centimeter. So the slope is 0, the negative slope is 0, the field is 0 in this region here. Okay, here's a quiz question. So in this quiz question, there were 2 more regions from 3 to 4 centimeters, 4 to 5 centimeters. It asks you to figure out the electrical fields in those regions. Let me post this. Okay. So I'll give you a few minutes to think about that and answer that. Okay, so maybe I'll move on with this. We want the potential in those two regions from 3 to 4 centimeters and 4 to 5 centimeters. And we know that we want the field in those two regions. The field is, again, the negative slope of the electrical potential. So if you see the slope is downhill, that means that it's going to be a positive field. Downhill slope is a negative slope. If you see the slope is uphill, then if the slope's uphill, that's a positive slope, then the potential's going to be, the field is going to be a negatively directed field. So look here, this is downhill, so this is going to be a positive field. This is uphill. This is going to be a negatively directed field. So this is downhill just like this was downhill. So this region 3 to 4, this region 1, 2 have the same directions of the fields. This region here, 4 to 5, is uphill. It's just like this region, 0 to 1 was uphill. So this region 1 and this region over here on the far right, they have the same direction for the electrical fields. And actually, the change in potential here is 30 volts, just like this was 30 volts. The change in potential from regions 4 to 5 centimeters, that's 30 volts, like this was 30 volts. And so the magnitudes of the fields are the same in these cases too. And so we end up with positive 30 volts per centimeter for the electric field in this region, 3 to 4 centimeters, negative 30 volts per centimeter for the electrical field in this region here. Okay. Let's talk about the electrical potential of point charges. We've talked about the electrical field of point charges, but let's see if we can picture both the potentials and the fields. We're going to write down equations for the electrical potentials of point charges. We're also going to learn how to sketch, visualize electrical potential of point charges. So both of those things. Okay. So in this slide here, I'm reminding you of the electrical field of a point charge, and I'm introducing the electrical potential of a point charge. I'm reminding you of the strength and the direction. I'm going to remind you of the direction of the electrical field. And I'm going to introduce the size and the sign of the electrical potential of a point charge. So if you look at this graph here, imagine the point charge is at the origin. We're going to imagine a positive charge. And this is your distance, radial distance from the charge, from 0 to 6 meters. We walked away. Vertically, I'm plotting Old friend, the electrical field, its strength, and new friend, the electrical potential, its size. So that's what's plotted vertically. So the field is in tangerine, or whatever this is, here, and the potential is in blue here. And the equations for the field and the potential are listed here. So this is that equation for the electrical field of the point charge. It depends on the charge. And it depends on the inverse square of the distance from it. And this is the corresponding equation for the electrical potential of a point charge. It also depends on the charge, not surprisingly. And it falls off as just the inverse of the distance from the point charge. Now, that field is the negative slope of that potential. Now, I'm just telling you that. So that 1 over r squared field is actually the negative slope of that 1 over r potential. So these fields and potentials are related in that way that we met in the previous slides. You can see, for example, right, in this region here of the field, that field is, let me say, in this region here of the potential, let's look at the potential. In this region here, the potential is downhill and is changing quickly. So if it's downhill, that's a negative slope, but the field is the negative of the slope, and so the field is positive, so that's the first thing. And the field is changing quickly because the potential is changing. The field is strong because the potential is changing quickly. Over here on the far right, here the potential is now changing gradually. So the field, which is the negative slope of the potential, firstly that potential field will be weak because this slope is just a gradual slope. And secondly, it's still downhill, so that's a negative slope, which means that the field is going to be positive. So it's a positive field here. So these two curves, the tangerine one is the negative slope of the blue one. And these two equations, the equation for the electrical field is the negative slope of the equation for the electrical potential. Here's how we sketch the potential. Like we learned to sketch the field with field lines, we sketch the potential with what we call contours of potential. So here's the positive charge in the center. Here are the familiar field lines in tangerine that represent the electrical field. They tell us where the field is strong because they're closely packed, where the field is weak because they're loosely packed. They tell us the direction of the field. Added to that sketch are these dashed blue lines. These dashed blue lines are contours of constant electric potential. So maybe this one here, this dashed blue line here, maybe that's 100 volts. Everywhere on that line is 100 volts. It's a contour of 100 volts. Actually, here it just looks like a circle, but really in 3 dimensions, it's a sphere of 100 volts, an equipotential surface of 100 volts surrounding the positive charge at the center. This circle here, this might be 50 volts. Everywhere around here is 50 volts. It's a contour of 50 volts. This might be 25 volts. Everywhere on that dashed line is 25 volts. This one might be 10 volts. Everywhere on that dashed line is 10 volts. And so we describe in a sketch, in a picture, we describe the potential with contours of equipotential. Like in a picture, we describe the field by lines of field. And so that's our schemes for sketching potentials and fields. You also see the relationship between the field and the potential. So where the field's strong, you'll tend to see the contours closely packed. Because the the field is strong, it's saying the potential is changing quickly. Where the field is weak, out here, you'll see the contours loosely packed. That's because if the field's weak, it means the potential's changing more slowly. And so that's why the contours are tightly packed at the center, they're much more loosely packed at the edge, because the field is strong at the center and weak at the edge. Here's another way we sometimes sketch the fields and the potentials in a kind of a three-dimensional topographic map type sketch of fields and potentials. Here's a positive charge at the center here. This vertical axis here and this surface here represents the electrical potential. So the potential is large if you're near the charge here. It's much closer to zero in this region far from the charge here. So this surface is kind of the potential, like the contours represented the potential. And then on this particular slide, the colors are representing the field. So the different colors represent different strengths of fields. So near the charge, the potential is changing quickly, has a big slope, so it's a strong field. I've indicated strong field with this red color. And then if you're far from the charge, right out here, the potential is changing slowly, so its slope is small. That means the field is small, and I've indicated small regions of small field with this color here. So the color coding, the transition from red through orange and yellow and green to blue, those are describing the changes in the strength of the field, the magnitude, the size of the field. We can do the same sort of things for electrical dipoles or other charge distributions. We can sketch the fields, sketch the potentials with these schemes of field lines, with these schemes of contours, with these topographic maps. So here's the field lines and the contours for the potential for an electric dipole. So this is our old friend, the electric dipole, like the water molecule. Here's the positive end, here's the negative end. Remember, the field lines sweep out of the positive charge, and many of them here are captured by the negative charge. And so the field is strong in this region near the charges. The field lines are closely packed. But because the field lines emerge from the positive charge, get captured by the negative charge, not many field lines escape to large distances. The field is really weak out here. These contours are the patterns of contours of equipotential. So they each one of those contours describes a path that is at exactly the same electrical potential. So, for example, this one here, this is close to the positive charge. Maybe this is 100 volts, plus 100 volts, surrounding a positive charge. There's one over here, it's close to the negative charge. Because it's a negative charge, think KQ over R, this would correspondingly to minus 100 volts. And then this next one around the positive charge, that might be 50 volts. Next one might be 25 volts. This one might be minus 50 volts. This one might be minus 25 volts. If you look at this picture, what I'm seeing is a mountain of electrical potential around the positive charge. I'm seeing this deep well, a valley of electrical potential around the negative charge. So whereas electrical fields have directions, left, right, up, down, electrical potentials they're just scalar quantities. They don't have directions, but they do have signs to them. Positive charge creates a positive potential. Negative charge creates a negative potential. And so this is a big hill here of potential. This is a deep valley of potential here. Here's a three-dimensional topographic map of the electric dipole. And it shows again, but in 3 dimensions, the pattern of the electrical potential, electrical field of electric dipole. So here's the positive charge. Here's the negative charge. Vertically, I'm plotting the electrical potential. So this sheet here, this distorted sheet, is representing the electrical potential everywhere in this world, in this space. We see that near the positive charge, the electrical potential is a large positive number. Near the negative charge, the electrical potential is a large negative number. So this really is a mountain of electrical potential. This really is a valley or a well of electrical potential. We see that the electrical potential away from the two charges is nearly zero. Those two potentials are kind of canceling one another out. One's positive, one's negative. If you're far from both of them, they cancel each other out. And then we see a color coding scheme for the field. So the field is strong here, and it's strong here in magenta here. The field is weak in this region here, and it's intermediate in this orange and yellow and green, and in this, whatever, this violet and some other color and some other color. You can see from the color map the regions of different strengths, different sizes of fields, and they're just the slopes, the negative slopes of the potential. Okay. Let's look at some example calculations. Enough pictures for one day. Let's actually do a calculation. In this example, I'm thinking about an arrangement of two charges, 2-point charges. There's a positive charge of 5 nanocoulombs that's on the left. There's a negative charge of 3 nanocoulombs that's on the right. They're separated by 35 centimeters. And we're going to be asked two questions. We're not going to be. We are asked two questions. What's the electrical potential at the center of that arrangement, the midpoint, due to the two charges in the arrangement? And what's the electrical energy associated with that arrangement of charges? What electrical energy did it cost to build that arrangement? So those are the two questions. No expense spared on this one. Here's one of the charges, Q1. Here's the other charge, Q2. They are 35 centimeters apart. We're interested in the potential at the midpoint. So I'm going to calculate in the first part the potential here. The second part, just to be clear, I start with these charges far away from one another, and I'm going to build this arrangement. I'm going to bring in one of the charges and place it here. I'm going to bring in the other charge and place it over here. And when I do that, when I build that arrangement, that's going to cost me some energy. And I'm going to figure out how much electrical energy I've stored in building that arrangement. Those charges were far away. They didn't know about each other. Now I brought them close together, a little couple there, and they know about each other, and there's a change in electrical energy by virtue of their changes of locations, and we're going to figure that out. Okay. Okay, let's do the handwriting test. So here's the question. We've got to find the potential at the midpoint and find the energy of the arrangement of these two charges. So let's start with find the potential at the midpoint. Let's see if I can do that. I always hit this brightness thing and everything goes haywire. Okay, so first part. We want the potential at this location here. So look, the first point is that this location is a distance, I'll call it R1, from the charge Q1, and a distance R2 from the charge Q2. Those distances are actually the same because it's the midpoint. So that charge on the left is going to create a potential at the midpoint midpoint. That charge on the right is going to create a potential at the midpoint, and we want to figure those two potentials of those two charges, and then we can use superposition to add up those potentials of those two charges to get the total potential at the midpoint. That's the whole idea here. What's nice about potentials? I've got a soft spot for potentials over fields. What's less nice about fields, potentials are scalars. I mean, they can have signs, plus and minus, but they are just numbers. Fields are vectors. They've got sizes, magnitudes, but also directions. So superposition for vector electrical fields is a more complicated problem than superposition for scalar electrical potentials. You'll see that here. So the total electrical potential, I call it V, is just the sum of the individual potentials, V2 and V1, of the two charges, Q2 and Q1. The potential of a point charge is just the charge divided by the distance you are from the charge, call that R1 for Q1, times the Coulomb constant. And then the same thing for the potential of charge 2. Its potential is Q2 divided by the distance that we are from Q2, it's R2 I called it, and times the Coulomb constant. All I got to do now is plug in these numbers. So I plug in the two charges, one's positive, one's negative. I plug in the two distances. They're both 0.75 meters, which is half of 0.35 meters. And I plug in the Coulomb constant, 9 times 10 to the 9, Newton meter squared, Coulomb squared. I'm saying all that because I'm going to avoid writing it here because we wouldn't be able to read it anyway. But if I plug in all those numbers, you find you get a positive potential for the positive charge, obviously. You're going to get a negative potential for the negative charge, obviously. They partially cancel one another out. Because the positive charge is bigger, though, it wins over the negative charge, which is smaller. And I ended up with 103 volts. So that's my calculation of the electrical potential. Okay, part B. Part B is what is the energy? Let me demonstrate the energy, and then we'll calculate it. So let's throw the midpoint away. Don't care about the midpoint anymore. But I do care about how I'm going to think about solving the energy of the arrangement of charges. Now they're very far away. So they're very far away, and because they're very far away from any other charges, they're just sitting in 0 volts of potential. And I'm going to move this one, Q1, to this location. But I moved it to a location that's still 0 volts because there's no charges in this little world here. Now I'm going to move this one that's at 0 volts, far away. Really, it's, in another room. And I'm going to bring it in and put it at its location. But now I'm placing it in the electrical potential of this charge here. So that will cost me some energy. So when we build this arrangement of charges, I'm really thinking about literally building it, bringing in the first charge, bringing in the second charge, adding up the energies that involves. So that's what I'm going to do on paper. Okay, so I'm going to call delta PE 1, subscript 1. That's the change in energy when I brought in the first charge, the one on the left-hand side. Now that change in potential energy is equal to the amount of charge that it owns times the change in potential that it experienced when I moved it. So it's Q1 delta V. This equation here is nothing other than the equation that we use to define potential. Now, in this case here, like Q1 is not 0, but actually the change in potential is 0 volts. It started out in a region on its own. It ended up in a region on its own. There was no change in potential. So this is actually 0. It costs me no energy to bring in that first charge. What about the second charge? I'm going to bring in the second charge. The amount, I'll call that illegible. I'll call it something illegible, but it actually is delta PE2. So that's the change in potential energy when I bring in the second charge. It's the amount of charge times the change in potential that that second charge experiences when I bring it in. It was at 0 volts, very far away, but now I'm bringing it into the neighborhood of the first charge and the potential of the first charge. And so the potential of the first charge is going to be K, Q1, divided by the distance we are from that charge. That distance is this separation of the charges, 0.35 meters. And so it does correspond to a change in energy when I bring in the second charge. If I fill in the charges here, Q1 and Q2, fill in the distance that they're separated by, the 0.35 meters, I get a number. And it's minus 0.39 times 10 to the minus 7, if I can read my own handwriting, joules, because it's an energy. And that's the energy that got transferred when I moved in the second charge. So if I wanted the energy, the entire arrangement, I'd have to add up these two energies. How much it costs me to bring in the first charge in energy units, how much it costs me to bring in the second charge in energy units. The first one was 0, the second one is non-zero. And so that total amount of energy in that arrangement of charge is actually negative 3.9 times 10 to the minus 7 joules. And so that's our answer to the second part of the question. Now, let me say a few words about that negative sign there. What does that mean? These are opposite charges, unlike charges. Opposite charges, unlike charges, attract one another. They want to be with each other. Because they want to be with each other, they're attracted to one another. The second charge just flew in towards the first charge. I didn't have to push it in towards the first charge. That negative sign means that if you wanted to pull these guys apart, if you wanted to separate this couple, you'd have to add energy. You'd have to add 3.7 joule 10 to the minus 7 joules to pull apart those charges. So this has a negative electrical potential energy. If those charges had been like charges, if they'd both been pluses or both been minuses, then it would have been quite different in building that arrangement. You would have put that first charge there, and then the second one, you would have had to struggle and push and push and push to bring that like charge in. That would be storing positive energy. That would be like a bomb ready to go off because it wants to fly apart. That couple doesn't want to be together. And so that would store positive energy, and it would just release it if the charges were released from your grid. Okay. No, that's not a slide, is it? Here's a second problem. I think I'm actually going to skip this one, and I'll post it. And I'm going to move on to some examples involving electrical energy. So that one I just skipped is another problem where we calculate the electrical potential and the electrical field. And I'll post that one in the notes. But because I'm a little short of time, because I rattle on about needless things, I'm feeling stressed and my heart rate's up, and so I'm going to jump to this section. Examples of electrical energy. Okay. So there's one thing that gets confusing about electrical energy and charges in electrical fields. And that thing is quite different from gravitational energy and masses in gravitational fields. And it comes about because of a fundamental difference that nobody understands between gravity and electricity. Is that gravity is always attractive. So masses always attract. Whereas in electricity, as we now know, there's both attraction and repulsion. So if you've got like charges, they repel one another. If you've got unlike charges, they attract one another. So in that way, electricity is a lot richer than gravity, where gravity is kind of boring, it's just attraction all the time. But electricity, you've got some action going on because you've got repulsion and attraction. So that makes it kind of a richer force. What was I going to say? Somehow completely forgot what that story was about. That story was about the following. So if you move two masses together, what you're always doing, because they attract one another, is releasing gravitational potential energy. And you would have to pull those masses apart. You would have to add gravitational potential energy to pull those masses apart. For the electrical situation, if you let a pair of unlike charges come together, a plus and minus, that also releases electrical potential energy. And you would have to add electrical potential to energy to pull them apart. But if you let two like charges, two positive charges, or two negative charges come together, then that actually stores electrical energy. That increases the electrical energy, and they want to fly apart, that would release the electrical energy. And so the complication with electricity that can get confusing, or it can lead you to make mistakes of signs and things like that, is that pushing two charges together can either increase or decrease the energy. Pulling two charges apart can either increase or decrease the electrical energy, depending on whether you've got like charges or unlike charges. So you have to be very careful about that. Here's kind of an example. Let's say we've got a positive plate over here on the left and a negative plate over here on the right. We've got electrical field between the two plates. If I release a positive charge here from near the left-hand side, it's going to be repelled from the left, attracted towards the right. It's going to move in the direction of the electrical field. It's rolling down the electrical potential hill. So positive charges roll down the potential hills. Think of those three-dimensional, beautiful, wonderful three-dimensional contours of electrical potential. Positive charges roll down those hills. Negative charge. Negative charge, if I put it over here on the right, it's going to be repelled by this negative charge. It's going to be attracted by this positive charge. It's actually going to be attracted over here towards the left. It's rolling up the electrical potential hill. So when a negative charge falls, when you release it and it just goes where it wants to go because it's being pushed by an electrical force, it actually rolls up the potential hills rather than down the potential hills. So imagine that case of the dipole. Positive charge, negative charge. Picture that in your mind, right? Imagine now sprinkling a load of other positive and negative charges in there. They're going to roll in different directions. Some of them, the positive ones, are going to be rolling down into the valley around the negative charge. Other ones, the positive ones, are going to be rolling up the hill towards the positive charge. So you've got them going up and downhill depending on whether they're positive or negative. Okay. In this question, we're going to we're going to observe. We're not going to release. We're going to observe a positive charge, it's a proton, as it travels from the left here at point A to the right here at point B. It's going to travel 3.2 centimeters. And it's going to be traveling through this region of uniform electrical field. So it moves from here to here, A to B, in the direction of the field. It's experiencing a force, an electrical force. Here's the equation for the force. Because that force is exerted towards the right, and it's moving towards the right, it's going to speed it up. So this proton's going to get faster. And what we're going to do is calculate these four things. We're going to calculate the change in potential between A and B, but then these things about the proton. What is the change in potential energy of the proton? What is the change in kinetic energy of the proton? What was the work done on the proton? Those three questions. Okay. I think I'm going to do this from my slide. First question is, what is the change in potential? So, to calculate the change in potential, I'm going to, again, remember that relation, that connection between the electrical potential and the electrical field. We said that the field is the negative slope of the potential. Now I'm using it again, but the other way around. I know the electrical field. I'm going to calculate the change in potential. The field was 375 newtons per coulomb. The distance moved, the distance between the two locations is 3.2 centimeters, 0.02 meters, 0.32 meters. And all I got to do to calculate the change in potential is figure the product, the negative product of the field and the displacement. And so I did that here. So this potential difference between A and B is 12 volts, negative 12 volts. This is lower potential at B. This is higher potential at A. So that's the change in potential. And I got that. I wanted to show that because that's an example of getting the potential change from the field rather than what we previously did, which was getting the field from the slope of the potential. You can go both ways between those two things. Okay. Now that change in potential, that del V, has nothing to do with the proton. So whether the proton's there or the proton's not there, that's the difference in potential between A and B. What has to do with the proton is if the proton is moving from A to B, how does its potential energy change? How does its kinetic energy change? What is the work done in changing those forms of energy? And so the next three parts depend on the proton. And we'll see the proton in these next three parts. Okay, change in potential energy. The proton is rolling down the potential hill. It's gone from higher up the mountain to lower down the mountain. The change in potential energy of the proton is its charge times the change in potential. That's the relationship. This is the equation, this is a famous one, that defined potential for us. Now we're going to use it to find the change in potential energy, knowing the change in the potential is the charge of the proton, positive 1.6 times 10 to the minus 19 coulombs, times the change in potential, that's minus 12 volts. We get this tiny negative change in energy of the proton. Change in potential energy of the proton. So, that proton is storing energy, electrical energy, by virtue of its location between the plates, and it's given up a little bit of that energy as it's moved away from the positive plate towards the negative plate by rolling down the potential hill. So the proton is releasing energy by potential energy, stored energy, by changing its position. What's the change in kinetic energy? Well, that energy didn't get destroyed. That energy just had its form changed. The loss in potential energy, stored potential energy, is a growth in kinetic energy associated with the motion. And so this guy here is just energy conservation. If I'm going to give up some potential energy, I'm going to correspondingly acquire some kinetic energy. That's the reason for the sign difference. And so if I've lost 1.9 times 10 to the minus joules of potential energy, I've acquired 1.9 joules 10 to the minus 18 joules of kinetic energy. The work that was done, the work that is done is simply the amount of energy that was transferred. That's just what it means. It was transferred by the electrical force. That's why I called it work subscript electrical. But it's the energy that got transferred from stored potential energy into moving kinetic energy. And